I want to share horror stories with you because many of you have been here in the horror story realm where things have seemed to be going really well, and then behind the door, don't look. So you've got something that you put together that you thought was going to work out pretty well. It's brilliant. It really works well. Everybody loves it. You've done all your cloud deployment. You've got your load balancers and your EC2s and all that cloud engineering stuff. It's great, only it actually isn't great. You got a whole lot of servers that are really slow, and what went wrong? You may have some kind of thing that is, it's, oh yeah, that's right, it's slow. You may have some analytical thing that you put together, and you've done all the regular data science, you've done your homework, you've got a model that is really, really good, and it has got a lot of explanatory power, and people really love it, but you discover that, when it comes to running the training, it's slow. So the first thing you do, the first thing everybody does, is you say, it's that damn Python. It's an interpreted language. We know the consequence of being an interpreted language means it's inherently slow, right? No, that's not really true at all. If you're using pandas or NumPy, it's really blazingly fast. You've got other problems, and the problems are not really language-based problems. So you do what everybody does nowadays, and I'm old, and I'm going to get out my lawn chair, and I'm going to sit in my lawn chair and shake my fist in helpless fury, because I remember the days before Stack Overflow, and none of you children remember those days when you had to look stuff up. Oh, wait, there's actually hi, old people. You had to look stuff up in paper books. Does anybody remember? So anyway, so you go to Stack Overflow and you say, what the heck, my thing is really bad. And everybody in Stack Overflow piles on the same useless advice, run profiling. No, I didn't want profiling. I wanted code I could copy and paste. This is the value proposition of Stack Overflow, is copy and paste code that I just have to copy and paste. I don't want to do thinking and analytical work on my code. This is crazy. But after you actually do the work, you discover what the problem is, that it really is the database. And so we wind up in horror movie trope world. There is a monster. It is in your base, and it is eating your dudes right now. And the monster is your database. This is the big bottleneck that big data all suffers from, is your database is sort of slow sometimes. And it's not your code. It's this other thing, the database thing, and it is largely opaque to most of us. I used to be a DBA, and so I had a certain privileged level of knowledge, and I can tell you databases are largely opaque. You can work with them for years and still never understand how all the moving parts and pieces fit together. So what I want to advise anybody who works with data, PyData, that would be pretty much all of us, that there is some hard work that needs to be done to defeat this monster. It will involve stress, but it also involves a fair amount of garden variety techniques that just have to be applied appropriately. I'm not going to go through the techniques here. I'm going to talk about some other related stuff, because the techniques, whether or not you add an index, is, in SQL it's a create index, or in Mongo it's a different kind of create statement for the index. Denormalization is a powerful, powerful tool, under-recognized, but when you look at a star schema design for analytical data, it's already denormalized. There's too much more you can do on that road. I/O concurrency is a thing everybody wants to do, and they hope it will help. If you're using Dask, in many cases, that happens sort of secretly and automagically, and it's a wonderful, wonderful thing. Data compression, it turns out, surprisingly can have a performance boost, but whether or not it does or doesn't is profiling question that you can't answer a priori. You have to do some experimentation. Oh wait, you have to do hard work. So the question is, what does that hard work look like? How do I find and kill that database monster? And the real question is there prevention techniques I can use? Spoiler alert, that's why I'm here. So in order to avoid having your project evolve into a horror movie trope, there are 2 pieces of advice, and they are these: simulate early and simulate often. And I want to emphasize the gigantic value of what some people call synthetic data. You're going to make up fake stuff to seed your database with, to experiment with before you start trying to use live data. By the time you get live data in there, it's sometimes a little late because now we have commitments and we're going to do real work with this database, and it's slow. And that's an awful position to be in, where people think it's usable, but it's not really, because the engineering work didn't really get done in the beginning. It's now getting done after the fact. The monster is already in the house eating your dudes, and you're trying to figure out what the monster even is. So, there's a Medium blog post here on our external blog about using synthetic data for some actual machine learning training exercises. Kind of a clever way of modeling something and generating data and using the modeled data as a training set. This is related, but it's not really the same thing. I want to talk more specifically about some more concrete things we can do in the simulation of the database as a whole. And I want to talk about things like looking behind the door and never running into the dark barn alone. I have trouble watching horror movies because it's like, duh, don't do that. There's things like, the trackless forest after dark. Like, who even, well, these things happen. The important thing, I think, is to stay with friends. I'm really reluctant even to split up from my partner in the grocery store. Why don't you go get the milk and the ice cream? No, that I know what happens when we split up, even in the grocery store. Not doing it. And the other thing is that the funny noises really, really matter a lot, because there are those things that you noticed in one of the early sprints where I had a test case with 20,000 rows and it took a long time. So instead of fix the root cause problem, which was the monster behind the door eating your dudes, you cut the test case down to 12 rows. All right, there was a funny noise and you ignored it. So of course the monster is eating you. Sidebar conversation on this that does come up occasionally. Some people will tell you that, really user experience is far more important than database scalability and whatnot. No, that is wrong. The UX may be important for a lot of things, but the bottom line is the data lasts forever. Nobody saves the user experience in an archive. 10 years from now, nobody is going to be wondering, which button did I click? No, they want the data. The data is what mattered. The data was the only thing that mattered. Therefore, we probably ought to invest some more time in the data engineering, the same way we invest a huge amount of time in user experience engineering. They're both really valuable. The data has a longer life, and therefore probably ought to be looked at more closely and clearly the whole life cycle of the project. So, 2 pieces of advice: simulate early, simulate often. I firmly believe, even if it's a web services thing, not necessarily big data, we're just like a person's filling in a form and we're going to go and run this thing that's going to start a Kubernetes cluster, and that's going to go run this other thing, and it's going to trigger off Airflow. Where was the data in that? It was just a transaction. Still, the data, that request to execute all of those moving pieces and parts, that mattered a lot. Build the data model for that as soon as you possibly can. Argue about the data model first, and argue about it, as we say later, often. Build a little nucleus of processing. This is Python world. The nucleus of processing ought to not be too much code. You just build some stuff and you play with it on your desktop as soon as you possibly can. I have, because I've been around for a few years, I used to work building military equipment, which meant you were building embedded software that went into like radars, which were going to be deployed in strange places. I built radars that were going to be deployed on the north slope of Alaska, and there would be no human being in that radar, completely unattended, very sophisticated machine. You spend a lot of time, like a year in software design, doing design walkthroughs and stuff like that before you commit to code. That's not this world. That was in the 1980s. It is now 2000 and something, 18, I guess. We can build software during the meeting where the users are standing there saying, I need to do this, that, and the other thing. Well, let me just hack some garbage together right here and now, because I can. So let me build the data model right away in some useful software form, ideally in Python, so that I can start putting together a performance testing environment right now, so that then I can go to the coffee shop where I'm supposed to be working, but I'm not really working, but then I can come back the next morning and I can put a realistic fake volume of simulated data in there and we can discuss rationally scalability. And we haven't invested too much in doing the wrong thing yet because we're still experimenting with Python. That is the strong suit of this tool set. So simulate early, as soon as you possibly can. Build the data model in some form, and I'll show you some techniques for this in a little bit. And simulate often. Every time the data model changes. And not like, every time. No, every time. I'm just going to add a field. It's just an integer. Who even cares? Stop. Will that really have no performance impact? Do you have measurements that show that just adding an integer to this table will have no impact? Get the measurements. Well, I'll add the integer. I ran some simulated data, 50 million rows. It hardly had any impact. It only ran for like a minute longer. All right, that's good. Now we have data. We can do that. Simulate often. If you have a little nucleus model that you're using for performance testing, then new features can be sort of folded into the little nucleus model, and you can have fake timing loops and fake processing loops and stuff because you don't want to write the whole app twice. But the point is, realistic volumes of data. This is the thing that gets all of us who were DBAs in a former life, gets all of us in trouble, is that the bigger your data, the more places it's spread around to, the more processing involved in getting the data out of its persistent storage into memory at all costs. It's all got hidden costs, and it's got derivative costs, and it's got confounding factors in the cost structure. It's very complicated and difficult to predict, so don't predict it. Simulate it. See what happens. And as I mentioned more than once, Python makes this particularly easy. So I want to talk a little bit about building candidate data models and building nuclei of processing. And I'm very, very excited by the way RESTful APIs and CRUD processing parallel each other. I think that's exciting stuff. Analytical ETL processing is also exciting, fun stuff. What you're going to want to build eventually is some kind of synthetic data generator. Sadly, I don't have a really cool open source project for this. There are some cool open source projects for data generators, and what I want to do is lay out how simple this is. Maybe you need somebody else's project, or maybe you just slap something together that will generate data for you and move on as quickly as you can. You're also going to want to eventually do some measurements, and the built-in time perf counter tell you everything you need to know about performance. You're not measuring a lot of subtle things. You're just trying to say, is this index structure on the database faster or slower than another candidate index structure? And you're just going to be running sort of ongoing experiments, trying different things. It's a lot like one of those basin hopping exercises where you're just going to try a bunch of different permutations until one of them is better. So if you've got a complicated data model done in like SQL Alchemy or the Django ORM or something like that, then you've got a really good data model. Those are pretty tight. They're not actually good enough for doing simulation, but they're okay as a starting place. If you're using data classes, Python 3.7, which is a very exciting thing, I'm loving those. They are, like the other things, okay. They're not all the way there. If you're using plain old Python objects or, you know, and like JSON or YAML serialization, they're okay. But all of these things are lacking some details. And the issue is that you generally only have minimal type definitions. String. How big a string? What kind of characters in the string? How much redundancy in the string? If I'm going to have a string representation of dates, they tend to begin with 1, followed by 9, or 2, followed by 0. And so indexing tends to go right down the old turlet because your strings all look a lot alike. If you just generate like rando data, they don't look a lot alike because your random number generators are really good. So ordinary SQL table definitions, ordinary sort of class, data class kind of type definitions in Python don't give you enough information. There's no ranges, there's no enumerated values, there's no patterns, there's really nothing. Primary and foreign key constraints is about all you have. You have a little bit of extra information in some places, but it's not enough. So my suggestion is, for everybody, you really want very, very narrow type specifications. And I think, so far, the optimal way to do this is start using JSON schema for, well, everything. So here's what I like to aim for, these kinds of things. I have... There's a blog post that shows what this model, hypothetical model class looks like. It's a meta class that uses JSON schema to validate the object at initialization time. And so the meta class initialization, the JSON schema validation that's built, it takes the YAML version of the type specification and confirms that the actual document built in Dunder and Knit fits the specification. If it fails to fit the specification, it raises an exception and you can't create an instance, and if it fits, it fits. And yay, we have an object. Performance is, of course, limited by the performance of the JSON schema validator, but the point is not the performance of creating objects, it's the retrieving them off the database is the important part. So in this case, I've used YAML notation to create the full thing, and I've got fairly narrow type definitions. So the suit here, the suit of a card, there are an enum, and those are the 4 strings. In front of God and everybody, that is the domain of values, no options, no choices, no doubts, no questions. So when it comes to building synthetic data, those are the 4 strings, no doubts. When it comes to building database indexes and things like that, when it comes to building search strings for your document store, those are the 4 values. And there's no 2 ways about this anymore. We're not talking rando strings or arbitrary strings or I don't know what kinds of strings. No, it's those 4 characters. And so that severely limits the way indexing is going to work. And you're going to have to make sure that you've got a data model that handles the indexing correctly over that domain as opposed to an imaginary domain or a general purpose domain. So I mentioned the model class there, uses the YAML module to turn the YAML into the document structure that the JSON schema validator uses. And, there's an abstract class that'll use the Dunder and Knit to validate the document. So the meta class looks a little bit like this. And I don't want to, like I say, I don't have a great a project for this, but it's really very straightforward in that I'm going to create this global variable, not a global variable, but a class level variable schema with the schema object in it. And I'm going to create another class level method there, validator, pulled right out of the JSON schema structure. The new version 3.0 of JSON schema now has up to draft 7 validators for all the new fancy features that they've been adding to the JSON schema specification. The 2.6 version only has up to draft 4. Your mileage will vary depending on what of those features you want to use, but we're going to need to extend the whole thing anyway, and I'll show you the extensions in a second. So here is sort of the superclass, just uses the meta class, and it provides the all-important dunder init, which does whatever initialization we're going to do. In this case, it's a subclass of dict, and it's going to run the validator on that dictionary. If the dictionary is valid according to the JSON schema validation, we're good. Otherwise, I don't know, type error. It's not good. And it looks like this when you use it. So I'm going to build an object, from a JSON string if I want to do that, or I could build the objects individually. I can do lots of things. But I get when I try to give it an invalid thing. So here I had suit is HEARTS, not the letter capital H. We get a type error. We get a detailed validation error out of JSON schema. So I have a pretty tight control over what the objects look like. The point is, of that stuff, the sort of sidebar is the JSON schema lets us provide the type, string, number, integer, that kind of thing. It gives us a place to put ranges in, which ordinary SQL doesn't have a great way to handle. It gives us enumerated values for strings, which SQL has no capability of specifying. It allows us to put in formats and other sorts of properties like regexes for strings so that we can really narrow those constraints around what that data looks like. And the text patterning, which is kind of awkward to work with, but it is certainly possible. So we can have a bunch of constraints around the data so that we know more specifically and very narrowly what that domain of data looks like. So once we have embraced JSON schema and maybe written a meta class or something to handle the JSON schema for us, now we can move on to the good bits. And the good bits are, I can leverage that JSON schema to generate synthetic data. That is the point, and it's not really very hard to do. The hardest part about it is deciding to use JSON schema in the first place, and then going through the agony of getting JSON schema specifications organized for your model objects, which some people object to and some people find difficult, and that's hard work. Well, it's all hard work. I'm sorry about that. But the monster is behind the door whether you do the work or not. The question is, are you going to get eaten by the monster behind the door? And the answer is do the work so that you don't get eaten. Within JSON schema, there's these 6 types of data here. There's a null. There are integers, and integers can have an enumerated set of values, and they can also have minimums and maximums. Numbers are the floating point version. Again, they can have an enumerated set of values and minimums and maximums. Strings, oh my God, strings are complicated. Duh. There are arrays, which are essentially Python lists, and objects, which are essentially Python dictionaries. What's going to happen is, as you start to think about how these schema objects work, is how you're going to generate fake data for them, what your source of that fake data might need to be, and how you're going to be using either random numbers or sets of pre-generated things to pick values according to these. Those are all the ones you have to solve for. There's not very many. It's not that complicated. So what you wind up with is code that could look something like this, where when I am looking at generating a fake record, the generate method down here at the bottom, what kind of schema is it? I'm going to actually plug the damn type into the middle of a string to build a function name on the fly. This is despicable code, by the way. MyPy hates you when you do this, but oh my God, it's so simple. I'm going to build the function, the method name on the fly, gen underscore whatever, string or null or integer or number or whatever, and then I'm just going to run that method and generate an example of that value. And so for arrays and objects, there's a recursion because you have to generate the individual items within the array or the object, and the other guys are just primitive. So generating an integer, you just pull out the range things and generate an integer. It's not that hard. Well, it's a little hard, but it's not that hard. And so the point being that once I have decided how I'm going to populate integers and strings and numbers and whatnot, I can generate synthetic data relatively simply by handing this generator class a JSON schema and turning it loose, and out drops documents. And so, I want a generator for a particular schema. I'm going to iterate over the documents generated, and I can do what I want. Load them up in YAML files, or write them out to JSON files, or stuff them in a Mongo database, or make CSVs out of them, or whatever it is I got to do. Do a bunch of Oracle inserts, whatever the right thing to do with that data is to populate my fake database with enough fake data that fits the schema really, really tightly. The integers are real integers in the right range. The floating point numbers are not between 0 and 1, but they're like dollar amounts or whatever it is that you needed to simulate to get your model to reflect the future reality of your application or the future reality of your data science processing. So you use this kind of tool set, the JSON schema, a little bit of Python code to simulate early and often to make sure your stuff is very likely to work, that if there is a monster behind the door, you know how big it is, you know how long the claws are, you know how many teeth it has, and you know what the growly noise is going to be like, so that you can then say, oh yeah, we didn't simulate that correctly, or oh yeah, we thought there was going to be these, but it turns out there were those, or oh yeah, we have irregular date formats. Some begin with 2 O's and some don't begin with 2 O's, and what do we do about the fact that the index doesn't work right anymore? These are things that we can explore in depth without having to be waking up at 2 in the morning for production problems because the job's not running. So really sophisticated data domains is where you're aiming with this. Just string, or just string with like a little pattern thing. No. Real deal is natural language kinds of items, names and addresses, comment text. Some of these things are not just simple rando things. You're going to have to write yourself some fairly sophisticated generators to make data that looks realistically like the stuff you're going to handle. So one of the ones that happens sometimes is string processing, where, if the schema had a constant value, you return the constant value. Duh. If the schema had an enum, you pick one out of the enum. And a flat choice is probably fine for the most part. If they gave you a format, well, now you're going to have to go format by format. Did the schema say the format is an email? I got to make a fake email. Did the schema say it was a fake URL? I got to make a fake URL. They don't look alike. They don't index the same. They don't have the same properties. They don't have the same lengths. So you're going to wind up with code like this sometimes where, oh, the format's a date time. Oh, God in heaven, I have to make a fake date. Well, it's not that hard to do, but the fact remains that you're not making a rando string, you're making a fake date string. So you're digging in fairly deeply to the types of data that you really expect to see in your database. And when you are doing more complicated database processing, like full text search and full text indexing, these are things that Mongo does for you, things that Oracle does for you. Random strings are not really completely appropriate. They have to look like the real thing so that your performance numbers are right. Credit card numbers are 10-digit strings. So you're going to wind up with the need for a random generator that looks like this, where I'm going to generate a string of digits of a given length. JSON schema is not really good at describing this. It's kind of okay at describing this, but you're going to have to ramp it up a little bit by doing some extensions. For things like names, people's names and stuff, I'm a big fan of just taking a big block of lorem ipsum text and slicing and dicing that to come up with words that are sort of Latin-based, of varying lengths, that look kind of realistic. They're not a lot like total names. I don't know if Ariel's in here now, but one of my coworkers, Ariel's got the most complicated name in the world with 2 different punctuation marks in it. 2 different punctuation marks, a hyphen and an apostrophe. And so for the love of God, simulating that is really hard, and it's often disappointing because he puts himself in his test data and, well, why didn't that validate? Oh, yeah, the Ariel problem. He has lots of punctuation marks in his name, and we forgot to account for that. How awkward. And he's right here listening to me. More awkward still. So you need to think about the data domains sometimes very deeply, and an ordinary generic synthetic data generator might not cover the bases very well, because you're going to have things that are deeper, more complicated, more problem specific. And reverse engineering the JSON schema to emit data isn't that hard. It's not really that difficult, so you can leverage JSON schema to generate your own fake data so that you can model your databases. So the way to get yourself in deep and profound trouble is to have faith that you already know the right solution. And it is, as a former practicing DBA, I can tell you there are many DBAs that will tell you many things about databases that are tried and true thing that they have a great deal of faith in, but no metrics. Awkward. So when you make assumptions, you make an ass out of you and me. No, wait, spell assumption. Make an ass out of you and umption. No, wait. Anyway. Making assumptions about the data is probably wrong. You probably ought to have real examples of the data. Making assumptions about the database performance is doubly wrong, because you've assumed the data, you've assumed the data model. Oh wait, maybe it's triply wrong. You've assumed how the query processing is going to go. You've made a lot of assumptions, none of which are validated by actual experience. So basically the problem is that hope is going to get you in a lot of trouble. Measurement is going to avoid the trouble. So look behind the door. Do not run into the darkened barn alone. It's the first sprint of the production increment. Why can't we do this right now? Maybe we should do a little engineering. Maybe a technical spike is better than racing into the darkened barn all by yourself. I strongly recommend technical spikes. The trackless forest. Well, we never did this before with this particular database product. Good idea. Yeah, let's just charge into the forest with no track in front of us. That'll work out well, I'm sure. Stay with your friends. And so you're going to have to work cooperatively with the analytic community that is using your data and the data sourcing community that's providing your data and making sure that the stuff goes into the database and comes out of the database in a respectable fashion. So this requires a lot of hard work and a lot of cooperation. And above all, do not dismiss the funny noises. That if we can't get a unit test or an integration test to work, this is indication that maybe we've got bigger engineering problems and we maybe should have had a spike sooner, which we can't go back and retroactively do. So maybe we need to slow something down, change course, maybe admit that version 1.0 is going to have scalability issues and take a divergent path so that version 1.1 doesn't have the same scalability issues. There's a lot of things we need to do, but the most important of them is not to dismiss the funny noises. That if it looks a little odd, measure. So simulate early and often. You can do this with Python classes really quickly, really easy. Data classes are fun and easy to use. Using JSON schema is even better. So you make yourself a little meta class, you put the JSON schema in there, you validate documents, and you can use the JSON schema to build synthetic data. And you then can actually gather hard performance data, real things, the real database on a real server. If it's cloud-based, you spin the server up, you run the thing, and you shut the server down. Yay, that's the most fun ever, because I can remember when we had to buy hardware, and you had to know in advance, a year in advance, how big a server you're supposed to buy. Based on what? I haven't even finished talking to the users. We don't even have UX stories yet, and you want me to specify hardware? Those were the bad old days. Now we can try it on for size and we can say, oh, the 64 core is doing pretty well, but I think I can get it down to a 32 core if I rearrange the indexes a little bit. Yes, and that is how you make the most money out of the technology that you have at hand. Thank you. Since it's lunchtime, I would prefer to take questions out in the hall if anybody has any, and I'll meet you out at the lunch line.